So thank you to the organizer for inviting me here. It's my first time also in this very nice place and conference. So the title sounds a little bit esoteric, but actually you will see it's related to the previous one. It will also be about the foundations of quantum mechanics. Maybe, as you will see, I'm more on the Hilbert side than on the Gruber side. Okay, so this is a sketch of the talk. I will skip it. So basically, my main idea and leading direction is that what can we tell about quantum mechanics after a loophole-free violation of Betz inequalities? So this should not come as a surprise because you don't know me, but these are my two first papers. They were visual letters about the famous aspect experiment, experimental Bell test in our cells. This was an experiment where I've been working for some years, and as you know, Alain Aspect introduced this idea of switching the direction of the polarizer in the Bell experiments, and then after a lot of efforts, several years of efforts, we finally demonstrated that Bell inequalities are violated with random switching, basically enforced Einstein causality. So this was not a perfect experiment, but surely it was the first, not violation of Betz inequality, but violation of Betz inequality with switching. So, okay, you guess that I was interested in Betz inequalities, but after that, it was a long time ago, I switched to other fields, single quantum fields, single photons, single atoms, Schrödinger cats. And so it took a lot of years to improve this experiment, and as you know, 33 years later, people completed what is called now loophole-free Bell test, and this is a paper by Alain Aspect himself in physics, by closing two loopholes at once, three experiments in 2015, removes the last goods that we should renounce local realism, which are Bell's hypothesis actually, and open the door to quantum information technology. Okay, so the conclusion of all these efforts are basically that Bell's hypotheses, which are typically summarized by local realism, don't work. So there is something wrong in Bell's hypothesis, so it should tell us something about the nature of reality, because this was the initial problem. So one can tell a lot of things about that. So I will try to go back to the very, very beginning. First, it's about philosophy, nature of reality. So, and so since we speak about philosophy, one has to specify what is our philosophical standpoint. So my point is what I call physical realism. So I believe in physical realism, which is simply that the purpose of physics is to study entities of the natural world existing independently from any particular observer's perception and obeying universal and intelligible rule. So this is my definition. So you have to stick to that. We keep it there. You may not agree, but this is my position, and I will stick to it. Now, if you look to this famous EPR paper, without any way disturbing the system, we can predict with certainty the value of physical quantities, and there exists an element of physical reality corresponding to this physical quantity. So, okay, this sounds very nice. This is reality, as defined by EPR. But if you follow this line, you end up to Betz inequalities, and Betz inequalities are violated. So, don't forget Bohr. So, Bohr told the very condition which defines the possible type of prediction regarding the future behavior of a system constitute an inherent element of the description of any phenomenon to which a term physical reality can be properly attached. Yes? Yes? Okay. I was reading more. Everybody should know that.
It sounded like an advertisement for drugs.
Okay, but this was just a quotation by Bohr. So my point is this thing, I speak slower, the very condition. So what are these very conditions required by Bohr to speak about the physical reality of quantum phenomena? So you see, this is EPR position, this is Bohr's position, and Bohr speaks about this very condition. And without this very condition, you cannot even speak about reality. But what are the very conditions? So I will try to tell it. So let's try to start again with this EPR sentence without any way disorder. Okay? So how should I correct that to make it true? And I claim it's very simple. You just have to add here, without in any way disturbing the system, never changing the context. So what is the context? It's simply the measurement apparatus, the specification of the parameter of the measurement apparatus. And if you add this, it does work. This is physical reality. And this thing, I call it a modality. So you simply add to the system, to the specification of the system, the specification of the measurement apparatus. And I claim that this is exactly this very condition required by Born. So now it fits, that is, it both fits with Einstein's certainty, because this is, I just claim that if you repeat the same measurement on the same system, you get the same result, with certainty. This is what I claim. And this I can call element of physical reality. So, so the object now, the big change is that the object is no more the system. The object is a system within a context. And this is non-classical in a crazy way, obviously, because now you cannot speak about an isolated system. If you want to specify an isolated system, you have to specify the context around. And then it is certain and reproducible. Otherwise, it isn't. So you see something like that. As soon as you have a system, you have a context around, and this context is like a shield, it's a measurement apparatus. You cannot access to the system without the context. And you need the context to specify properties, elements of physical reality. So obviously, there is an obvious criticism. If I split the context and the system here, there is a separation. Otherwise, I could not split them, define them. But this is not a problem for me. I will come back to that. So this thing is called the Heisenberg cut. It's very famous. But this is not really a problem because the modality is defined in terms of both the system and the context. So this is external to the observer, and the system cannot include the context. I will show that on the next slide. So this comes to a very famous statement that I like very much by Perez and Zurek. Quantum mechanics can explain anything, but not everything. It doesn't explain the whole world. It explains subsystems within context. So if you do a little bit of ontology, so classically you have system, observer, context. Contexts are just tools. They are measurement apparatus. So once you have measured your system, you can ignore the context. To this there is a universal context. So you can let the observer, classically, can know the real physical property of the system, and the context is just a tool. Now, usual quantum ontology, the trouble is that you untangle everything with everything. So as soon as you make measurements, you untangle the system with the context and the context with the observer, and then, okay, you hit second physical reality, and then you go to many world interpretation. So through successive entangling interaction and unitary evolution, the system will include everything. Okay. So this is a standard way, in some sense, that I dismiss it something. So my way is that simply the object is a system within the context, because this is an object. And so the observer is external to that. So obviously observers agree between themselves because they all see if they have access to the same system and the same context, they get the same result. And so the context appears aware as a shield between the system and the observer. And the modalities, the elements of physical reality, are attributed jointly to the system and the context. So now, why is it impossible to ignore the context? Because in classical physics, we ignore the context. So what prevents to have unique context where all modalities would be defined? So within a given context, the modalities are mutually exclusive. If I make a measurement, the results are mutually exclusive. If one of them is true, the other one are wrong. And then in another context, I will get other modalities. And what is quantum mechanical in some sense is that modalities taken from different contexts are not mutually exclusive. If I take polarization like that and the polarization like that, so these two are mutually exclusive in a given context, these two are mutually exclusive, but this one and this one are not. So incompatible modalities are non-classical, I will come back to that, and classically it should be possible to get more details and to distinguish them, but quantum mechanically is not possible. And so my sort of hint of what is quantum, quantum is just that. Is that quantization principle. Quantum is quantum, basically. It's that the number of n of mutually exclusive modalities is a property of the quantum system and is independent of the context. For a given quantum system, for instance, 2 qubits, you always have only 4 mutually exclusive measurement results. Whatever measurement you do. I will come back to that. Okay, and then I can reconstruct my stuff. So I have a first axiom, there are modalities. Okay, this is associated with a complete state of physical quantities. The modality is attributed to a system within a context. This I will come back. Then the main point, there are indistinguishable modalities that are mutually exclusive in a given context, and then this value of n, called the dimension, and it will be the dimension of the hyperspec, obviously, is a characteristic property of a given quantum system. And also, if you change context, you change continuously context. That is, you rotate your polarizer or Stern Dirac can be rotated continuously. It's very naive mathematics. Okay, so this is essential, obviously. This is a little bit more surprising, this extra contextuality, so I will explain. So if you look at a Bell experiment, for instance, you know that you have two orientations on one side, two orientations on one side, so that's four possible contexts. And then, if you have these four possible contexts, you have quantum mechanics and you evaluate Bell's inequalities. So what are Bell's inequalities? Basically, it's to assume that you have a global context. And then you can split, that is, if you have A prime plus, then A can be plus or minus. And then you try to give probabilities to all these events. And if you do that, you get Bell's inequalities. It's called counterfactuality. There are many different demonstrations, but this is a simple demonstration of Bell's inequalities. So here you have, as I said, 4 mutual exclusive for 2 qubits, 2 spins 1/2. In each context, you evaluate Bell's inequalities. Here you try to build 16 mutually exclusive modalities in a global context. You look for more details. You have A, which is plus or minus, but you want also to specify A prime. So you split your context in pieces, and it's impossible. It's forbidden by my postulate. So then you obey the inequality, but you disagree with quantum mechanics. Okay, so you may tell, okay, so we have 4 different contexts, and that's it. But no, that's not it. Because if I take my 2 qubits or 2 spin 1/2, these are 4 different contexts, different ones. So here I just measure my 2 spins along Z, so that I have this standard flow result. Now here I measure the total spin, I can do that. So as you know, elementary coupling of angular momenta, you have 2 values for the total spin, 0, 1, and then n equal minus 0, 1. So you have again 4 steps. Whatever you do, you have 4 steps. This is my basic postulate. And you can also measure Bell state, which are all entangled state. So these are 4 contexts. These are 3 other contexts. There are infinitely many contexts, and they vary continuously, as I said by my postulate. Okay, so now what's the trick? The trick is that you may tell, okay, contexts are independent contexts, and I can do whatever I want between contexts. But this is not true, because the certainty of a modality can be transferred between contexts. For instance, if you take these 2 states, actually, they are the same state. They are different modalities, but the same state, in the sense that if I get this result for sure in this context, I will get this result for sure in this context. You remember, coupling of angular momenta plus gives 1. So they are connected with certainty, despite the fact that these 2 contexts are incompatible. They don't commute. Same thing here. These 2 things are the same. Same thing here, you go to entangled state, but this is an entangled state also. And actually the same state is the same of Kate, but it's different modalities because they belong to different contexts. Okay, so you see there is actually, despite the fact that the contexts are non-commuting, incompatible, they share some modalities. They share certainties. And this is what I call extra contextuality. So when a system interacts in succession in different contexts, certainty and repeatability can be transferred. And this I call extra contextuality, define an equivalence class, as I call extravalence. And so it's easy to realize that if you want, you need probability, because you have to measure all that, I will come back to that later, then the probability depends on the extravalence class. That is the little drawing here. If I have 2 extravalent modalities here and 2 extravalent modalities here, all these probabilities that connect this one to this one are equal. So it's a simple reasoning, it's only one in our paper. So all the probabilities represented by this dashed line are equal. So actually this idea of extravalent modalities tells you that probability assignments are non-contextual in quantum mechanics, which is true. I will give more details later. So the probability does not belong to the modality. It belongs to the extravalent class That is to the psi in some sense. But psi is not a state. I will go back to that later. Okay, a little jump to Cohen-Specker. So it's sort of a generalization of what I said. You know, it's a Cohen-Specker theorem by Cabello. I have one. This is one. I have 9 contexts. So 4 modalities in each context, as before. And then I add extravalent modalities. So same colors mean that these 2 modalities are connected with certainty. And I can do that with in quantum mechanics. So I want to do that. I want one and only one modality true for each context. This is my basic postulate. If a modality is true in one context, the extravalent modality, with the same colors, is true in the other context. I want that also. Now let's try to add all modality to give a truth value to all modalities, 0 or 1. So any possible modalities must either be true, realized, or wrong, not realized. And this is impossible. This is Cohen-Specker theorem. So it's very easy to see that since I have not 9 slots, only 1 true per slot, I must have 9 times true. But then if they go par pairs, they should be an even number of slots. So, and 9 is not even. So it's impossible. So it's just Cohen-Specker theorem. So Cohen-Specker theorem tells that there is no non-contextual hidden variable theory. It's impossible to attribute truth value to all my modalities together. And so I must give up one of these 3 hypotheses. So which one should I give up? The first one I want, it's a postulate. Second one I want, it's a postulate. So I'll keep this one. So what does that mean? It means that it's impossible, support empirical evidence, to give truth value to all modalities. So you need probabilities, otherwise you are stuck. So if you don't believe me, here is the full stuff. These are all the quantum states. So you see that in a 4-dimensional inverse space, you get all these states. Now you see, for example, if this one is true also. By extravalence, you get 0 and 1s, but you cannot get only 0 and 1. It's impossible. So what you get, this is a quantum mechanical values, basically. And you get probabilities everywhere. But still, you fulfill extravalence. That is, for example, if this one is true, this one with the same color is true also. And this one is true, all the other ones are wrong, and the same color are wrong also. So it works perfectly well. That is, you just propagate information based on extra contextuality and the fact that you have only one true result per context. Is it clear? Okay, so these were no-go theorem. So you should not go to Bell's inequalities, they are wrong. You should not go to Cohen-Specker. It's wrong also. So now forget quantum mechanics and ask, how can we make sure that there are only n mutually exclusive modality in any context? The certainty of a modality can be transferred between contexts. This is what I want. So I can use an inductive reasoning, try to make a mathematical theory which does that. So how should I do? Well, you know the reason. Let's attribute an n by n projector to an extravalence class with orthogonal projector mutually exclusive modality in a context, same projector mutually certain modality in an extravalence class. Then, if I want probabilities, this probability should depend on the projector, that is another extravalence class, where f depends on the initial state, Pn is a projector, and also I want just by standard probabilities for mutually exclusive results in the context, that if I add the probability in the context for any orthogonal state, that is the probability sum to 1 when the projector sum to identity in the context. Okay, and what I claim is that if I do that, I get quantum mechanics by using 2 very powerful theorems, which are the famous Uhlhorn and Gleason theorem. So Uhlhorn theorem, which is not well known, this is really surprising to get from that. It's quite a decent theorem. If I have 2 contexts, each with orthogonal projectors, I express the projector in one context as a projector in the other context. But the basic thing is that I should preserve the orthogonality. Since the projector has to be orthogonal in any context, I have to preserve orthogonality. Only orthogonality. Not the modulus, nothing else. I just want to make my projector to stay orthogonal. Then the only way to do that is as using unitary or anti-unitary transformation. This is quite impressive.
When was that for?
Sorry?
How old is this theorem?
It's from the 60s. I have a slide after that. It's a fantastic theorem. You know, if you preserve the scalar product, you get unitary transform. If you preserve the modulus of the scalar product, you get the same result. It's Wigner's theorem. But if you only preserve the scalar product when it is 0, without caring about the norm, you already get unitary and anti-unitary transformation. This is this incredible Uhlhorn theorem, which is basically unknown, except by people who know that. Who know it. There are many papers on Uhlhorn theorem, but it seems to be completely ignored by the physicist community. So then I get unitary transform. Oh, I'm pretty happy. Then you probably noticed, if you know that my previous requirements actually are just the hypothesis of Gleason's theorem. So I also get Born's rule. So I have unitary and Born's rule. So this, and it's deductive, it's theorems. So if you swallow what I told before, here you are stuck, and you get quantum mechanics. So this, we published that recently in Entropy. So this is a mathematical form of Uhlhorn theorem. So this is Uhlhorn, you see, it's a 62. It's actually difficult to find. Okay, but if I can send it to you, I got it from my library. And there are many papers about Uhlhorn theorem, extension, etc., for instance, by this guy. And Gleason, everybody knows Gleason, so Gleason is hard to read, but I recommend this paper by Cook, Kins, and Moran, which is sort of a user-friendly Gleason. So these theorems are really powerful theorems, that is, even with tiny hypotheses, they demonstrate very strong results, but they are very very hard to demonstrate. Okay, anyway, so I'm happy I got quantum mechanics. But you see that now a projector does not define the modality. It defines the equivalence class, extravalence class of modalities. So if I want a modality, what should I get? Well, with my projector, so I conclude that psi is incomplete. Because if you want to complete psi, you must specify the whole observable. That is, this psi, you should have an operator. This is just a spectral theorem. With Cn, this one, which belongs to the set of eigenstate. So you need both these things to define a modality. And so I do agree with Einstein, psi is incomplete as long as you don't specify the context. It's not what Einstein thought, but this is a nice way to complete. Okay, but then the formalism should be able to describe both the quantum system and the classical context, and then both sides of the infamous Heisenberg. For this thing, there is this paper, in Entropy, okay, which is in the little booklet. I'm happy that Entropy, put that as an important recent paper. Okay. Anyway, so now I want a formalism which describes both system and context. So how to do that? So I already digged in all literature, and I found a fantastic von Neumann paper, 1939, on infinite direct products, which is also completely unknown by physicists, but well known by mathematicians. And what does von Neumann say? Just take the limit of an infinite tensor product. You make a tensor product, but let's make a countable infinity of subsystem in the tensor product. So, okay, and every time we say, okay, choose the wave function. No, this is completely wrong. What Neumann said, infinite tensor product differ essentially from the finite one, in which the infinite tensor product splits up into incomplete tensor products. That's what we call now sectors. What happens could be described in quantum mechanical terminology as a splitting up of the tensor product into non-intercompleting system of states corresponding to the incomplete direct products quoted. Otherwise, say, if you take the infinite limit of your tensor product, your Hilbert space blows up and splits in separable subsystems. It's sectorized. So I recommend this paper, it's on the way. Okay, so now I can do it. I just consider that my whole system is a tensor product of a usual projector. But for the context, obviously, it's not a usual projector otherwise. So I have to use this mysterious times 3, Alan Cohen type stuff of projector, but I think it works pretty well. And so this provides a unified global picture for everything. So obviously, this context is absolutely obvious, horrible, I would say. But the trick is that since all these contexts are orthogonal in type 3 algebra, there is no need to specify all the details of the context. Actually, it's impossible. It would be trying to describe a polarizer by all the atoms in the polarizer, which makes no sense. So we just need to specify the orientation, and this will be enough. Okay, and the description applies to any isolated system within the context, and so it's complete, but again, it's not a theory of everything. It's a theory of anything. Yes, so this is almost my last slide, take-home message. Okay, so usually one uses decoherence attributed to information loss, quantum Darwinism, Zurek, etc. What I tell is that if you just jump to infinity, which is a mathematical jump, I don't claim that there is infinity in physics, but in mathematics we are always using infinities, even when you calculate the derivative, then, well, it's not so bad. And so, this is a quotation. In summary, let us return to our main theme. The role that remains to the infinity is solely that of an ID which may unintentionally trust within the framework erected by our theory. Who wrote that? Can you guess? Yes. So he also wrote that. No one shall drive us out of the paradise which counters creative force. And this is David Hilbert in 1925. So my sort of hint is that physicists should play with infinities. We are losing something by refusing to play with infinities. Let's follow counters. Okay, these are my co-workers. Thank you for your attention.
Thank you for a very elegant talk. I found there were many echoes of things I happened to know about, and I so much enjoyed trying to translate you into what I happened to, from the philosophy end, to have heard about. Things like the von Neumann 1939 is mentioned by Hartle in 1968 in his The Quantum Mechanics of Individual Systems, when he's considering these infinite experiments. And the Uhlhorn is known as a strong version of Wigner's theorem in the mathematical physics community.
Yes.
But I really admired so much of what you were saying. I have a philosophy suggestion. The word modality in philosophy always means the general topic of possibility and impossibility and necessity. And I think eventuality is a good word for your modality, because it has, it's like the word event, and it has that, you said a modality is the possible values of a physical quantity.
It's a certain and repeatable value. I take your comment, thank you. In this field, all words have already been used by many people with different meanings. You take locality, contextuality, all of them, they have a full set of meanings. So it's a really delicate issue, but okay, thank you.
May I argue in favor of modality, because Spinoza defines a mode to be a thing that is defined relative to something else, and you're using modality basically in that notion. So even though it's
the name comes from a course in École Polytechnique. I'm teaching quantum mechanics in École Polytechnique, and previous teacher, Jean-Louis Balban, used when you make just a Stern-Gerlach experiment and you have different results, he called that modalities. And I think it's a good name. I kept it.
Going away from philosophy, I think once you decide to describe your world in terms of classical probabilities, many things get actually much easier. For example, you're saying that something is real with the probability 1. Well, for the EPR setting, what is real is the correlation between both things. Physicists should we know that correlations can be as real as individual spin values. I mean, we have many examples of that. Actually, surprising that Einstein did not realize this. Another question is the basic assumption of Bell's inequalities, which is often not realized, is that you have classical correlation functions for all observables. This is in general not true. I give you a simple example. Take temperature. Temperature is definitely something we observe, but it's a property of a probability distribution. So it doesn't have a fixed value in any one of the microscopic states of the molecules. So there is no classical correlation function, let's say, between the temperature and the position of some particularly signaled molecule. I think it is too simple to say that classical observables are all commuting observables. We know a lot of examples, if you go, for example, to the transfer matrix formalism, that you have operators in classical physics as well. And of course you have observables that are represented by non-commuting operators, and it's simply not true that all classical correlations or all correlations in classical physics are necessarily given by the classical correlation functions that supposes that both observables have a fixed value in the microstates. This is simply not true, and that's a very basic assumption of Bell's inequalities.
If you want to go to what goes wrong in Bell's inequalities, this is written in this paper in some details. My point of view, what goes wrong in Bell's inequalities, because okay, local realism is wrong, but if you try to split local realism in locality and realism, you are sort of dead.
It's a much simpler assumption. It's the assumption that you have classical correlation functions.
Okay, so please have a look at this paper, and I sort of explain in my framework what goes wrong in Bell's demonstration, and it's related to something which is called predictive incompleteness, which was introduced by John Jarrett some years ago. But okay, it was not the topic of this talk, so...
We have time for one more question.
Yes, thank you. I just wonder whether you've ever considered the Everett interpretation of quantum mechanics in relation to Bell's inequality. There are many people who have the view, and I'm among them, that there is no non-locality in Bell's sense in the Everett interpretation. So I just wonder whether that makes any difference to any of your reasoning.
I have a big trouble now with Everett interpretation, which is just this Bodman paper. Obviously, Everett people will never admit to take infinitely. But I repeat, I don't assume that physics is infinite. I just take the mathematical limit of infinite tensor product, and what I get is not at all a universal wave function. It's a sectorized algebra. So you see, that's sort of the limiting case of tensor product of many systems. Is not a universal wave function. It's a type 3 incomplete algebra, so it's completely split up. So it becomes classical in some sense. And so, given that, I have a hard time reconciling with Everett interpretation. But okay, this is very controversial. This is for the copy break.
Thank you, Philip. Let's thank both speakers.